All right. So we were talking about Schrodinger equation. We have not derived it, as I've said. So there's some plausibility argument that led to this equation. It's a second order linear differential equation, which the wave function is a solution of that equation. And what do we do with the wave function? The wave function will allow us to calculate the probability, and there is also a quantity called as a probability current density. So just to so this minus h square over 2m d2 psi dx2 plus some Vx psi is equal to E psi, and mostly we'll be talking about the time independent Schrodinger equation, and so this will give us the solution will give us this psi, and from psi we'll get the probability density which we have written it earlier. So this could in principle be function of x and t, but here we are not considering the time dependence, and we'll separately learn how to time evolve a wave function. That is, as time progresses, what's the form of the wave function or how it evolves, which would include a time factor. Okay. So right now we are dropping the time index, which is t, and we'll go ahead with this psi of x. So this is your probability density, and there's another quantity called as Jx, which is called as the probability current density, which has a form which is 2mi and psi star d psi dx minus psi d psi star dx, and they put together follow a continuity equation, which I'll show you at some point of time. I'm keeping that probably one of the last classes for a finishing up, or rather tying all the loose ends. This is called as a probability current density. This has a relationship with this, which is called as the equation of continuity, and so on and so forth. Okay, so this is equal to this del p del t and things like that, and so this divergence of this current, so we'll write it as a small j, this j that we have written now, and so on. Okay, we'll see all of that. So let us now see the important part, that is how to solve this equation for a given problem, for a given form of Vx. But before that, just to say the basic postulates of quantum mechanics, and so the one of the basic postulate is of course this psi, which gives you the it describes the behavior of the particle, and it must be single valued. So this psi of x must be single valued, which means that at a given value of x, it must be having one value, unique value, such that the probability density doesn't become ambiguous somewhere in space. So it cannot happen that there are two probabilities at a given space point for the particle to exist. Okay, so it's single valued, that's why, and it's also square integrable. So what is meaning of square integrable? It means you take the mod square of that. I've told you that this is in general complex, and this from minus infinity to plus infinity should be equal to 1. This is called as the square integrability of the wave function, that um, sort of normalizes the probability. So the normalization of psi requires the probability to be normalized as well. So they are connected, and that's why the psi should be normalized, and so on. And and this psi, as we have seen, that this psi, if you write it in that notation, Dirac notation, so this is equal to some alpha n, and some basis kets which are written like that. So there are a large, so this n really goes from 0 to infinity, or you can call it 1 to infinity, doesn't matter. So it's like alpha 1 phi 1 plus a alpha 2 phi 2 and alpha 3 phi 3 and so on and so forth. It goes to infinite number of terms, and when you try to calculate certain observable, then that value of that observable comes with an eigenvalue, so to say. So the result of that observable, when measurement is done on a system, it comes with an observable comes with a probability which is mod square of this. So suppose you calculate the energy of the system, or try to find the energy of the system, you'll have to operate it by the Hamiltonian, and and if you do this, psi x Hamiltonian psi x, then it should give you energy with alpha 1 square E1 plus alpha 2 square E2 and so on and so forth. Okay, so you'll get a energy E1 corresponding to this basis ket phi 1, E2 with phi 2, but with these probabilities. The probabilities are given by the mod square of these things, and in general they are complex as well. So you get a mod square would give you a real number. Okay, so let's just go to something more sort of easier topics, or rather solution of these equation for a given type of potential. Okay, and this is, as I told you, that this is a linear differential equation. There is no term such as psi square or psi star or d psi dx into psi. So that's why it's linear, and it's second order. Because of this, the highest power of the derivative or the highest derivative that exists in the equation is that of second order. All right. So there are two boundary conditions which and these boundary conditions are called as psi should be continuous across a potential discontinuity. I'll tell you what a potential discontinuity means. Let me write it clearly here. Potential discontinuity. The second one, this is called as the Dirichlet boundary condition. Okay, again, mathematician's name, Dirichlet boundary condition. And there's another one which is the derivative of psi. Okay, and you know that space derivative is linked to something like a slope, etc. And this should also be continuous across a, I'll add a term which is called as a finite potential discontinuity. So I'll write it POT and then discontinuity. So these are the two boundary conditions. Why we need boundary conditions? Because any of these differential equations, when you solve them, they come with unknown coefficients, and these unknown coefficients gives a family of solutions, and any member of that family is a valid solution. But if you want to know it concretely, then you need to have a boundary condition to fix those coefficients, and fixing those coefficients are very important, and that's what we would see here, that because it's a second order equation, you need to fix it with two boundary conditions, and these are the two boundary conditions that you see here, that is psi must be continuous and the d psi dx must also be continuous. Okay. So let us start with the simplest one. okay. And the simplest one is a free particle, that is the potential is equal to 0. So, we take this is called as an infinite potential well, and this is the first case that you can think of. So, what is an infinite potential well? So, this is a potential well, okay. So, V is equal to 0 here. Say the well extends from x equal to 0 to x equal to some L, okay. L is the length of the box. So, this is an infinite potential well, it is a one dimensional system. The particle is somewhere inside the well, it does not feel any potential, which means it is a free particle. But because of the presence of the boundaries, the energy will not be just like a free particle which we have seen in classical mechanics, p square by 2m. It will still be p square by 2m, but the p will be quantized and will get quantized energy levels for this particular problem. Okay. So, how do we do that thing? And in no way the particle can escape outside. So, that is why we have shown the V to be going to infinity at both 0 and L, okay. So, it cannot escape. So, I will write down this equation minus h square by 2m d2 psi dx2 equal to E psi, and that is a very simple equation to solve, because you see the solution is like harmonic waves. So, this will be like d2 psi dx2 is equal to minus 2 me by h cross square. Just to remind you, m is the mass of the particle, E is the total energy of the particle. Here the total energy means the kinetic energy only, and this is your equation that you need to solve. Oh, well, psi is a function of x, that is known, okay. And if you take this as minus k square psi, where k is equal to the wave vector, which is equal to 2 me by h cross square. So, which means m, h cross etc. are constants. So, k is proportional to root over of E. So, if you say that, then your psi of x has a solution which is a sine kx plus a b cosine kx, and we should have been happy with that. But now, let us see the boundary conditions. Here the problem is so simple that even one boundary condition at both the boundaries, like boundary condition on the psi itself, at both the boundaries would be good enough to solve this problem, because you will see that one of the solutions becomes incorrect if you apply just the psi continuity of psi. And what is it? The boundary condition is that psi 0 equal to 0, because a wave function has to vanish at this left end. And why? Because if it does not vanish, if it continues to the left of this barrier, then there will be a probability for the particle to exist outside the barrier, which we have said in no uncertain terms that such a possibility does not exist. So, that is equal to 0 here, and it is same as at the L, at the boundary L. So, we do not need to invoke the decide if, but in more complicated problems we will of course need that, and we do not need it here because we reduce it to one solution only. Let us go to this board and try to see the solution. Okay. This one, it says that psi 0, psi at x equal to 0 is 0. So, that tells you that B cannot, I mean the cosine cannot be a solution, okay. Cosine cannot be a solution. So, the only solution that can exist is a sine solution. So, it is a sine kx, okay. And that's the reason that you don't need a d psi dx anymore. We just reduce it to one constant and one coefficient which needs to be determined, okay. So very well. So the solution is this. And how do we calculate A? Now you invoke the normalization condition. And how do we invoke that? We simply invoke it by minus infinity to plus infinity. But in this case, there is nothing about infinity and I mean plus minus infinity. My region of integration could simply be 0 to L. Okay, it's actually from minus infinity to plus infinity, but anywhere from minus infinity to 0, the wave function is identically equal to 0. So I don't need to consider that region. And similarly for from L equal to 0 to n, I mean L equal from x equal to L to x equal to infinity, the wave function is again equal to 0, and that's why you don't need to consider that. So this is the condition that should find A, and if I put it there, in principle, this is a mod square as I said, but here of course it's a real function, so you can simply write psi squared. So this is equal to a square, a is a constant, and a sine square kx and dx and so on. So this should normalize this. But there is a small, we can also find a condition on K from this condition that psi of L is equal to 0, which means the sine KL is equal to 0, which means that sine, and now this is equal to sine, I mean 0 means it's equal to n pi, okay. So this K is equal to n pi over L. Okay, so this, let's put a n here so that we know that this K index, which is a wave vector, goes with a quantum number n. This n is actually equal to 1, 2, 3, 4 and all the integers. Okay, so that's your quantization of K. And just going back to this K relation with with E, which is equal to 2me by h cross square. Now I'll just put back this n here just to say that there is K is quantized with in this form, which is n pi over L, which means that K can only take values which are pi over L, 2 pi over L, 3 pi over L and so on. Okay, so this tells you that your En is equal to n square pi square h cross square by 2m L square. Okay, very nicely, these are energies of the particle inside the well. So I mean, you see, n starts from 1 here, because if n starts from 0, then the particle is not there. Okay, so we are not talking about particles. So the lowest energy is equal to pi square h cross square by 2 ml square. The next one is not 2 pi square but 4 pi square h cross square by 2 ml square. Then the next one would be 9. So it's 1, 4, 9, etc., in terms of pi square h cross square by 2 ml square. So we can, while doing this calculation, we can put this K equal to n pi over L, and we get this A as root over 2 by L. I leave that simple integration for you to do. So the wave function is now the problem is known. So psi is equal to root over 2 by L sine n pi x by L, and the energies are n square pi square h cross square over 2m L square. Okay, so these are called as the Eigen solutions of the problem. The eigen values are given by En, and the wave function, you can again put a n there. So the lowest lying wave function or the lowest lying eigenfunction is called as a ground state. So if someone asks you what's the ground state of this, and the ground state is root 2 by L sine pi x by L, and the first excited state would be when n equal to 2. So that's root 2 by L sine 2 pi x by L, and so on and so forth, and the corresponding energies will be scaled as as this n square pi square h cross square by 2m L square. Okay, so that sounds perfectly fine, and so let us let's have it here, and let us draw the energy levels and the eigenfunctions, at least for the first 2-3 of them. Okay, so the first one, which is sine pi x by L, has only nodes at 0 and L. So it is like this. So that's the lowest one, corresponding to n equal to 1. So the next one is 4 pi square h cross square, which is equal to this. It has to vanish. So it has nodes there. And the 9 pi square, that's the third one, is like this. Okay, it's symmetric, of course. And so on. So so this is n equal to 1, this is n equal to 2, this is n equal to 3, and n equal to 4, and so on. So it shows more and more oscillations as you go to larger and larger energies. And so what is it like if you go to very large energies? So that's called as the correspondence principle. So correspondence principle says that what is your delta n En for large n. What I mean is that for two consecutive, what's the difference between two consecutive energy levels for large n, and that can be found because this is equal to n plus 1 whole square minus n square divided by 2m L square, and so on. So this is equal to n plus n square plus 1 plus 2n minus n square, and so on. So the n square will cancel, and this is equal to 2n plus 1. But what are more meaningful quantities is that you divide it by En, which means that what is the fractional energy or the relative energy difference for large n. So we'll have to divide it by n square, which means that it is like 2 over n plus 1 over n square, which of course goes to 0 for large n. Okay, the sort of dominant quantity is 2 over n, because 1 over n would be even smaller for n. Well, I mean, for large n, in fact, this goes to 0 faster. Okay, so that's the dominant one, not this one. Anyway, so that's it goes to 0. So which means that in the classical limit, when n is very large, the energy difference between successive levels go to 0, and this is what we know, that in classical mechanics a particle can take any energy, and you can increase the energy of the system infinitesimally to a value which is larger than that. Okay, all right. And so how do we if you know that your this all these psi's form a complete set of states where psi n is equal to some alpha n phi n, where these phi n's are the sine n pi x by L. Okay, and you know that a measurement of the first energy, which is the lowest energy, will yield E1, and then the next one will yield the E2, and then the next one will yield E3, and so on. So one can actually calculate the expectation value of the Hamiltonian, which is equal to a psi h psi, and this will eventually, if you write it, it will eventually give you sum over n alpha n mod square and multiplied by en and so on. Okay, I leave that small algebra. It's just one step there. So you put h equal to alpha n phi n, and h acting on phi n is going to give me en phi n. Okay, this is just what I said, that you can calculate the energy of this acting on the phi n. So phi 1 is sine pi x by L. That will give you E1, which is what you know from there, and so on. So which means that if you make the measurement of energy or the expectation value of energy, will give you all these energy eigenstates E1, E2, E3, etc. with probabilities given by alpha 1 square, alpha 2 square, alpha 3 square. Incidentally, here the alpha, which is the coefficient, which is that a of the wave function, is that is not the coefficient. I mean, this alpha n mod square will be the probability, and a is the wave function, the normalization of the wave function. Okay. All right. So this is one important problem in quantum mechanics, the free particle problem, so to say. And the free particle problem is, even though it's easy, but it still requires you to work all these things out. I make the problem slightly more complicated, or whatever you say, maybe a little tricky, and say that I don't do anything to this problem excepting that I shift it on towards the left by minus L by 2, which means that this end is not 0, but it's L by 2, and the right end is at plus L by 2. Okay, so it was from minus L to plus L, and I simply shift it so that it now is from minus L by 2 to plus L by 2. And the question is that, is there anything that happens? Okay, and yes, I mean, there is a good deal of things that happen there, and let us see that what is what can be learned from that. Okay. So what we can do is the following, that now we can call it, instead of calling it psi n, we can call each one of those things as unx, okay, which are the basis functions or of the phi n's. Basically, these are nothing but the phi n's. Okay, so these are the phi n's. So let's write a phi n x. For this, it's equal to root over 2 by L and sine. Now I'm going to shift the coordinate x by minus L by 2. So this is n pi over L x minus L by 2. Okay, so this is the wave function now. But this wave function is quite important, because if you open this up, you'll have a term which is sine n pi x by L and cosine n pi over 2 and so on, and there'll be another term which is cosine n pi x by L and sine n pi by 2. So this will be like root over 2 by L sine n pi x by L cos n pi by 2 and minus cos n pi x over L and sine n pi by 2. And what happens is that for n equal to even, for even n, that's like 2, 4, 6, 8, etc. Cos n pi by 2, it's equal to minus 1 whole to the power n by 2. You can take a n by 2 there, and sine n pi by 2 is equal to 0. okay, which means that the second term won't be there, and this will give rise to a minus 1 whole to the power n by 2, and because n is even, this term will give you a 1. So this, the wave function is psi of x equal to root over 2 by L sine n pi x by L. That's your for n even, and now you can do a quickly n equal to odd, and if you do n equal to odd, then your sine is equal to 0, and your sine n pi by 2, uh, sine n pi by 2 is equal to minus 1 whole to the power n by 2, uh, and so this is and cosine of n pi by 2 is equal to 0, and then what you have is you have a term, so this is not n by 2, it's odd. So these are like 1, 3, 5, 7 and so on. So this minus 1 whole to the power that, and there is a minus sign. So that put together, so this will give you a minus sign and this will give you a minus sign. And so this is equal to, for n equal to odd, it's equal to root over 2 by L cosine n pi x by L. Okay. So now this gives you two classes of solution. One for n equal to even, when it's like the normal one, but now sine 2 pi x by L, sine 3 pi x, sine 3 pi will not be allowed, sine 4 pi x by L, sine 6 pi x by L. Whereas for n equal to odd, it will be root over 2 by L cosine pi x by L, cosine 3 pi x by L, and so on and so forth. Okay. So the ground state of the system is given by now the cosine term instead of the sine term. The first excited state is the sine term. The second excited state is again the cosine term. The third excited state is the sine term, and so on and so forth. You start from n equal to 1, call it a ground state, n equal to 2, call it a first excited state, n equal to 3, call it a second excited state, and so on. Okay. Now this gives rise to a concept called as parity, which is what I said yesterday, the inversion symmetry. As you stand in front of a mirror, your hand, left hand becomes right hand and vice versa. So this problem from minus L by 2 to plus L by 2 has this additional sort of feature or characteristic called as parity. So there is a, if you, it's a 0, then you have the there is a right left symmetry. So corresponding to a point here, there is another point here, okay, and so on. Okay, so importantly, we have been able to solve it for the normal problem from 0 to L by 2 and also from minus L by 2 to plus L by 2. And it's a, we didn't have to use both the boundary conditions because the problem was simple and we had one solutions, either sine or cos, and we saw that in the 0 to L there is just sine solution, and in the minus L by 2 to plus L by 2 there is sine and cos both, depending on whether it's even or odd. Now how do we calculate the expectation value of x, and why do we need the expectation value of x? We need the expectation value of x because we may need to convince ourselves that there is a quantum particle inside a potential well. The uncertainty relation is obeyed, okay, is followed. So this will be equal to psi star, okay, let me write it first in your Dirac notation. So this is equal to your psi x psi and so on. Of course, for the symmetric problem, this is equal to 0, but you can for the 0 to L, it doesn't need to be. So this is x and sine square pi x n pi x by L dx and so on. And from 0 to L, we are going back to the original problem, and you can solve this integral. I'll not solve it for you, but you please do that. And similarly, you can calculate x square, which is equal to 0 to L x square sine square n pi x by L. And the problem could be even simplified further if someone tells you that the particle is in its ground state, which means that then you'll put n equal to 1. Okay, and do this solution. Similarly, your P can be found out by using, so P as a minus IH cross del del X. This is a little, you have to be a little careful because you cannot just simply write psi square here. So you have a minus IH cross d dx, or it's also called del del X psi dx, again from minus infinity to plus infinity, and it reduces to 0 to L, because for everywhere else the wave function vanishes. There's no point in calculating the momentum. And similarly, the p square would be simply equal to a minus 0 to L a psi star and a minus IH cross d dx, and again a minus IH cross d dx. So this minus I and minus I will give you a plus I square, and the plus I square and h cross square d square dx square. So it's like minus h cross square dt2 dx2 and operating on the psi x, and then integrate it. Okay. Once you do that, then you can get a delta x, which is equal to root over x square average minus x average square, and you get a delta p is equal to root over p square minus p average square, and this you multiply both of them, and that should come to of the scale of h cross. Okay, I mean the relationship is h cross by 2, I mean delta x into delta p, which you can check for this case. Okay, it's a simplest problem, but teaches you something quite important. Okay. So let me do the second problem, which is little more involved, but again is quite informative. And here we are actually going to include a potential. All right. So I take a one-dimensional potential. So this is called as a potential step. So it's like a step like this, and it infinitely goes, and the discontinuity is at x equal to 0. So this is x less than 0, and this is x greater than 0. Okay. So as if you encounter a step, okay, in front of you while you're moving, and we have of course energy to overcome that barrier and go on to the next step. But suppose a small baby who cannot climb steps or stairs is given to climb that, and of course the baby doesn't have energy to go anywhere on top of the hill. So we are just talking about now a quantum particle which has energy, either the energy of the particle. So the particle comes from x less than 0 regime. Okay, so this region is where the particle initially comes from, and it's more interesting to talk about a E which is less than the height of the potential. Let's call it as V naught. Okay, so E less than V naught. So let's call that as case 1, and the most important case where E is less than V naught. Okay, and but E is greater than 0, which means we are not talking about negative energies. Negative energies are also possible, and they are called as bound states. Okay. All right. So let us now do this problem. and so there is a finite discontinuity there. So you have to write down the solution of the equation on the left side and on the right hand side of x equal to 0, match the solutions at x equal to 0, match the derivative of the solutions at x equal to 0, and find the coefficients. Or even if you cannot solve for the coefficients unambiguously, you should at least find the ratio of these coefficients. All right. So the solution is or the equation is written as the first case, that is d2 psi. I'm simplifying it because I have already shown you earlier, and this is equal to k square psi. Okay, and this is equal to 0. You can write it as k1 square psi, where k1 is equal to root over 2 me by h cross square, and we are talking about region 1, which is x less than 0. Okay, x less than 0 is like a free particle. It comes and incidents on the barrier, and you would say that for a classical particle there is no hope for the particle to transmit to the other side. But here it's just not a particle, there is a wave character associated with this, and waves can actually go into this region as a dying wave. That is, it's an exponentially decaying solution, and this is what we are going to see. Okay, so this region 2 is x greater than 0, and in x greater than 0, you have a d2 psi dx2, and there is a minus k2 square psi, where k2 is actually root over 2m v naught minus e by h cross square. So from your experience, you know that this one is like the harmonic oscillator solutions. So you will have solutions which are like sine kx or cosine kx, but now we are talking about infinite space on the left and infinite space on the right, which means that this side, the left side, is completely open for the particle so that it can escape to minus infinity, and also the particle, if possible, can escape to plus infinity. Of course, it doesn't escape. But so here, instead of writing the sine and cosine solutions, we'll be writing the exponential ikx and exponential minus ikx solutions, which will also oscillate at plus minus infinity. Okay, or at least minus infinity, there will be a solution. So the solution in region 1 is written as psi of x equal to a exponential ik1x plus b exponential minus ik1x. Okay, so that's the traveling wave solution, free particle solution. And in region 2, we'll have a solution which is like psi of x. So let's write psi 1 and psi 2. So this is equal to c exponential k2 x plus a d exponential minus k2x. Okay. Now, so this is for region left region, and this is for the right region. And A, B, C, D's are constants which need to be determined. Okay. All right. So now what happens is that this part is a solution that will blow up at x equal to infinity. So if there is an exponential function which at x equal to infinity will keep growing, such a solution is very bad for us. Why? Because it doesn't help in the normalizability of the probability. That is, the wave function itself cannot be normalized if one term blows up, because you see the mod square of the wave function integrated over all space will have to become 1. If some term diverges, then it will prohibit the integral to become 1. So, this term has to be dropped because it is not, even if it is mathematically allowed, but it is not physically allowed, and we are doing physics. So, that is why this term can be dropped. The oscillating solutions are fine, this solution is fine, this solution is fine because the wave can actually go to 0 at x equal to infinity. You do not have to go to infinity, it will sort of go to 0 at some value of x, or go to very small values and will not bother you. So, so our solution is a exponential. So, let me just remove this now, and the k1 and k2 are written there. So, first let me use the continuity of psi. So, psi at x equal to 0 minus, it's equal to psi at x equal to 0 plus. Okay. What I mean is that just left of the barrier and just right of the barrier, the wave function should be smoothly connected. Okay. There shouldn't be any discontinuity there. And if that happens, then I get a plus b, it's equal to d, and I k1. So, this is from continuity of psi, and this is from the continuity of d psi dx. That is, I calculate d psi dx and do this, and this is equal to a minus b, it's equal to minus k2 d. Okay. So, these are the two solutions, rather two equations that I get by the continuity of psi and the continuity of d psi dx, which is like saying that d psi dx at x equal to 0 minus it's equal to d psi dx at x equal to 0 plus. Okay. So, that is your thing. Now, what we can do is that we can solve for this a, which is equal to 1 plus. Now, you have 3 coefficients but 2 unknowns, or 3 constants and 2 unknowns. So, you cannot solve it all 3 of them independently. Okay. What you can do is that you can get a ratio of 2 in terms of the third one. So, this is what we do. It's I k2 by k1, and this is divided by 2 into d, and this is b is equal to 1 minus I k2 by k1 divided by 2 into d. Okay. So, see that this is a and b are calculated, which means that I am calculating the coefficients on the left region. The left region is given by AB and the right region is given by the coefficient D. Okay. All right. So, so this is your A and B. So, B by A, this is equal to 1 minus I k2 by k1 divided by 1 plus I k2 by k1. Now, you see this has a modulo 1, which means that b by a mod square is equal to 1. Okay. So, if you multiply this by this complex conjugate, then you will get it equal to 1, which allows us to write a b by a, it's equal to exponential I alpha, where alpha is because I mean, if something has a mod 1, then you can write it as exponential I alpha, because exponential I alpha into exponential minus I alpha will give you 1 as well, and this alpha is then defined as 2 tan inverse minus V naught by E. I'm just skipping a few steps which you should fill up, but this has to be done because there's a large number of things to be completed for this course, and minus 1 and so on whole to the power half. So, that's your alpha, and the d by a, so that's equal to 2 divided by 1 plus I k2 by k 1. So, this is equal to 2 divided by 1 plus I V naught by E minus 1 whole to the power half, and this is equal to 1 plus exponential I alpha. Please do that, then you will get satisfaction that you have learned this. So your ratio of the coefficients B by A, that's the ratio on the left of the discontinuity is like exponential I alpha. Alpha is given by this, and D by A is 1 plus exponential I alpha, and you can simply so now we can define the reflection coefficient, which is equal to B mod square by A mod square, okay, or B by A mod square basically. And the transmission coefficient is D mod square by A mod square, and so on. So this in fact will give you, so R plus T, you can check that this is equal to 1 because of this so you can take a d by A mod square, which will be 1 plus exponential minus alpha. So when you take a d by A mod square, so this will be 1 plus exponential I alpha into 1 minus exponential minus I alpha. So this will be like 1 plus exponential I alpha plus exponential minus I alpha plus 1, sorry, minus 1, and they will cancel, and this will give rise to, so there will be a sine, cosine alpha, and then you can put this there, and then you can check this, that R plus T is equal to 1, which means that the reflectance plus transmittance should be equal to 1. Okay. So what is the physical picture? Let's come to the physical picture of this thing. So here the wave function will oscillate, and it will come here and it will go down like this. The wave function here is a incident wave and a reflected wave, and because they interfere, there will be an interference pattern on the left, which is here, and as it enters, it will show a behavior which is like this, and it will go down. So this is called as a evanescent wave or a decaying solution inside, and it doesn't bother us. So this is at x equal to 0. Something very interesting happens, which I will leave it to you, that if you calculate J, which is equal to, I have given you the form, which is psi star d psi dx minus psi d psi star dx. This is equal to some velocity of the particle and divided by a square minus b square, and since a square minus b square equal to a square is same as b square, a mod square is same as b mod square, so this is equal to 0, and it's also equal to 0 for, so this is for x less than a, and this is for it's also of course equal to 0 for x greater than a, and the reason is very simple, because the wave function is completely real. If the wave function is real, your psi star and psi are same, so these two terms become same, so there is a minus sign, so they'll cancel each other, so there'll be no current anywhere. So and who's cancelling the current on the left? Right, we understand that there is no current, there is no propagating particle in the right of the barrier when the energy is less than V naught, but the current, the incident current is exactly cancelling with the reflected current on the left of the barrier. Okay. So, this is what it happens. So, the current actually vanishes everywhere, which now what happens when V naught is equal to infinity. So, there is one of the limiting cases that V naught goes to infinity, that is this height discontinuity becomes larger and larger, in which case you have B by A goes to -1 and D by A goes to 0 from those relations that we have given. And if that happens, you can understand the entire incident wave will be reflected back and there will be no transmission, and that is what it says, which makes sense. If you make the potential discontinuity to be infinitely large, the particle can never go through. Very interestingly, if you solve this problem, I will not do that, but I will let you do this solution, that I will tell you the result of that. So, if you take this E to be now greater than V0, so this is E to be greater than V0, so let us call it case 2. Okay. Now you would wonder that why would there be, I mean, if the particle is larger than the barrier height, then why would why would there be a difference between classical and quantum mechanics? It can go through the barrier easily. Yes, true. And there will be I there solution. You can write it with a plus sign, because there is nothing to reflect back. So, it will be exponential I k2x in that case. Okay, and you can go ahead with the solution that we have provided for this case, match the solutions at the boundaries, and so on and so forth. And there is very important one difference between E greater than 0 and E greater than V0 and E less than V0. In E greater than V0, you will see that there is current that exists everywhere. So, current is not 0, which I showed that the current is equal to 0 there. and I will not do this, but I will let you do this, that this it just falls like this. So, this is the reflectance or the reflection coefficient as a function of E by V0. So, very interestingly, I mean, this is E by V0 equal to 1. So, the reflectance, as you increase energy, it gets, if E is is much greater than V0, the reflection coefficient becomes 0. So, the entire particle will get transmitted as the E becomes larger and larger than V0. Okay. All right. So, there are many other questions. What I will do is that I will do the last problem for now, which is another class of problem that is called as the delta function potential. And why is this problem important? The problem is important because this is an infinite discontinuity. So, you have a potential which is like this. So, at x equal to 0, it goes to infinity, but delta functions are integral, the integral is well behaved, which means the delta of x. So, if we call it a v equal to v naught delta of x, it goes to infinity, but delta x dx at all space is equal to 1. Okay. So, delta function is a somewhat quite interesting function, so to say, which shows such a property that it by itself goes to infinity, but the integral is not. Okay. So, but this is very important thing for us in quantum mechanics on the boundary conditions. So, the boundary conditions say that psi at x equal to 0 minus is psi at x equal to 0 plus. This is valid here also, but for infinite potential discontinuity, the derivatives are not continuous. So, d psi dx at x equal to 0 plus or 0 minus is not equal to d psi dx at x equal to 0 plus. Okay, but that is not a problem for us because we know what is the amount of discontinuity, and so we need to find what is this. If it is not equal to this, then what is this? If we know what is this, then it's as good as knowing that there is a relationship, and that's what we will do. So let me just take a v naught delta x and we'll sort of write down minus h square by 2m d2 psi dx2 plus a v naught delta x psi, well, not required here, so it's equal to e psi. I multiplied by minus 2m by h cross square, so this becomes d2 psi dx2, and I have it's equal to 2m by h cross square v naught delta x minus e psi. Okay, now I integrated this both the sides of this equation and write this as d dx of d psi dx. Okay, and we do it from minus infinity, minus epsilon to x equal to plus epsilon. So it's 0 minus to 0 plus dx, and this is simple because v naught, well, v naught can go out, delta x dx, okay, from minus 0 minus to 0 plus, actually from minus infinity to plus infinity, it doesn't matter, minus 2me by h cross square and psi dx from minus 0 minus to 0 plus. Okay. Now you see the last term is equal to 0 because psi is continuous. Psi at x equal to 0 minus is equal to psi at x equal to 0 plus. So this is equal to 0. This one is equal to 1. So this is 2m v naught by h cross square, and now I get this, exactly this thing. The left hand side gives me this, and so the potential or the gradient has a discontinuity that is given by this 2m v naught by h cross square. I'll quickly try to do a problem very quickly. Just give me one moment. आके बैठो 5 मिनट ले सकता हूँ, एक हो जाएगा. So we'll do this delta function problem. I just redefined the scale that v naught, let me take it as minus, I'll take an attractive delta function. So it's minus lambda h cross square by 2m, just to get rid of all these other things. And so this one will give me d2 psi dx2 minus 2me h cross square psi, it's equal to minus lambda delta x psi, and so on. Okay, so that's the equation that you have to solve, and now we now can apply both the boundary conditions because we know that psi is continuous across the infinite discontinuity, as well as d psi dx, even though it's not continuous, it's discontinuous, but it's discontinuous by a known amount. Okay, so what I'll do is that I'll write this down as, so 2me by h cross square is replaced by say a k1, or you can simply write it as k. I just written it as k1 square, and so this one your psi at x0, or rather a d psi dx at x equal to 0 minus a d psi dx at x equal to 0 plus it's equal to minus lambda psi at 0, and so one can write down the solutions as psi of x equal to exponential minus k1x for x greater than 0, and it's equal to exponential k1x for x less than 0. All right. So this we've taken the coefficient to be same, because you see psi is continuous at x equal to 0. So the coefficients have to be same, and so k1 is of course given by this. So this number 2, that's this equation. So let's call this equation as 2, this as 1, and this as 3. So if you from 2 one gets that, so minus 2k1 is equal to minus lambda, so k1 is equal to lambda over 2. Okay, so that gives the so we have taken this lambda, so we that h square etc m etc they have gone. This gives the equation for the energy of the particle, which an attractive delta function potential. The attractive has got nothing different than the repulsive. You just have to change the sign, everything else will fall through, and this is what so we have shown 3 kinds of potential problems here so far. We'll show more. One is there is no potential, that's a free particle inside an infinite potential barrier, and then we have shown a potential step. We have considered E greater than V0, E less than V0, where V0 is the height of the potential, and then we have looked at a delta function potential. We'll carry out with more the definition, or rather the examples of these potential problems, solution of Schrodinger equation, and finally we'll be doing also a harmonic oscillator, which is part of the syllabus. All right.